Hello everyone. Here's a video on metals and alloys. When we talk about metals, we have to talk about the metallic bonding model. And as I mentioned here, metals are weird. You can bend them, they can conduct electricity and heat, you can bend them right back. They hold their valence electrons very weakly in something called the sea of electrons. Okay, so let's talk about this sea of electron model. Okay, so the valence electrons, again, all the electrons that are held on the outside are held quite loosely. So again, recall that metallic atoms lose electrons easily, and a metallic compound valence electrons are what are called delocalized. These delocalized electrons, these valence electrons, can move anywhere they want, as much as they want. And since they flow freely, this allows a couple things to happen. First of all, if they can flow freely, this sea of electrons can be directed. And if they can be directed perhaps down a wire or across a metal wire, a metal flat sheet, you can get electricity to flow. Electricity is the flow of electrons, or current is the flow of electrons. Okay, so again, the electrons flow freely in what's called a sea of electrons between the positively charged nuclei. And you can see that in this picture, these electrons can go anywhere they want. Okay, at any one point in time, those electrons can just jump onto any atom because, again, we have positively charged nuclei being attracted to the sea of electrons, which are, again, delocalized. They don't belong to any one particular atom. So again, this is a very weird chemical property. So since metals are malleable and ductile, you can read the definitions there. Malleable is flat sheets, ductile is you can pull them into wires. Deforming the solid does not change the environmental surrounding of the metallic nuclei. In other words, these things can move past each other, flow past each other, again, if you hammer them into a flat sheet, because, again, they're not locked in these bonds that are so rigid where electrons are shared or transferred. Again, it's a sea of electrons versus the positive nuclei that are being attracted to each other. Okay. Now, this is kind of a cool fact. Why are metals shiny? Because the free-flowing electrons are excited by the interaction with the photons, which is the light, causing those electrons to vibrate and reflect the light. So if we take a look a bit further into more of a I don't know, a quantum theory of electrons, of atoms, we see that the electrons, if you shine a light on a piece of metal, those electrons are excited. They jump in and out. Okay, so they interact with those photons and cause that light to vibrate just based on the light to reflect based on the vibrations. All right, real quick, alloys, which are mixtures of metals, come in a couple different versions. We have what is called a heterogeneous alloy, an intermetallic alloy, and a homogeneous alloy. Okay, taking a look at this picture right here, notice we're mixing tin, copper, and zinc. Okay, so let's take a look at these things and what they're called and how we're going to interpret them. Okay, if we talk about a homogeneous alloy, these are alloys with the same crystal lattice structure as the one of the constituent elements. In other words, take a look at the pure metal. Okay, so let's say this is all copper. This is all copper. Probably shouldn't have chose red there. Okay, now what I'm going to do is I'm going to substitute in a metal that in this case we'll take a look. It's called a substitutional alloy, but the metal that I'm going to substitute in there is close in size. Okay, so notice the blue is slightly less than the red. What this does is cause a strengthening or perhaps a different coloring. And perhaps copper, if I say the red one's copper, this might be zinc. Okay, so zinc is actually just slightly smaller than copper. Okay, so that's called a substitutional alloy. Now, if we take a look at this and we now substitute in something that is, so notice, substitutional substitutes, for example, if this is this one here and here, I've substituted that one out and put the blue one in. So it's replacement. Whereas interstitial, inter means between, and now I'm adding things in between, okay, which causes different properties to occur. Okay, and you notice if you go one step further, you can have substitutional and interstitial at the same time. Okay, which again gives us different physical and chemical properties. So substitutional alloys, brass and copper and zinc. Excuse me, brass is copper and zinc. Here's the pure metal, here's the copper and zinc. So any of you guys in band and you play a brass instrument, that's what it is. Copper and tin is bronze. Okay, and again, this is substituting of similar sizes. Interstitial is now in between. Okay, steel, actually stainless steel, is iron and carbon. Okay, now this makes it a little bit more brittle, but also strengthens it at the same time. Okay, so it just depends on the amount of steel and carbon that are mixed together. Okay, actually I believe stainless steel. There we go. There's iron, carbon, nickel, and chromium. I knew there was something else in it. Okay, so interstitial. Okay, so this would be more like stainless steel. Okay. All right. So sterling silver is composed of silver and copper. What type of alloy is this? Well, silver and copper are very close in size, so we're going to probably look at a substitutional alloy. It's probably B. Okay. And I guess that's all I have. So, okay. Again, email me with questions, ask questions in class, whatever you guys need.